Hello, everyone. Hope you're doing well. In a different place now because my computer was dying. And so I had to hook it up indoors. And here we are once again to talk about another theorem here, the Arzela-Ascoli theorem, something that we read about a little bit before we started talking about some of the stuff regarding the Stone-Weierstrass theorem, looking at in particular, how can we say that the continuous functions in a compact metric space have a particular dense set? Now, I was thinking about what I had said back in the previous video, and I may have said something that kind of would have led people down the wrong path if I didn't immediately correct myself. So I'm here to do that first. I believe I may have mentioned at some point when I was discussing that the set of all polynomials is separable, meaning that there is a countable dense set inside of it, that I would have said, oh, this is true of any continuous functions on a compact set. And that is not necessarily the case. The polynomials are a special case because we can get that algebra to be something that is countable. And it's very possible that as you go through and take a look here at these continuous functions on a compact set, you may get that any possible algebra that you get on that space is still uncountable, that you have just too many things going on in that. So the fact is that the set of all polynomials is a very special case. It helps us see that the continuous functions are a separable space and hence have a very nice little size restriction there. However, it's not necessarily the case that this works for any compact metric space. So what we end up doing in those sorts of situations, if we need something a bit more manageable, then what we end up doing is attempting to restrict our study to something that is a strict subset of these continuous functions. Typically, the right size from our study to take a look at are the compact subsets of these continuous functions on compact spaces. Now, that's two levels of compact here, and we're going to be using compactness at both levels. The set X is going to be a compact set for what we're going to be talking about today. But we're also going to be looking at compact subsets of the continuous functions, and that's compactness at the level of functions. So not only at the level of the metric space that we're working on, but also on the level of the functions over that metric space. Now, we choose compact subsets rather than separable ones for two reasons. One, as we're about to see in this theorem, that there's a very neat characterization that involves the equicontinuity that we talked about at the beginning of last week. And two, compact metric spaces are separable. So they have the right size. They are manageable types of spaces. And that's our very first thing that we'll do is we'll go through in this proposition to show that compact metric spaces are indeed separable. And you can choose the countable dense set in such a way so that there is a finite subset of sets that are inside, or is this a finite subset A sub delta of A, so that I didn't even need this in here. I wrote that in there because I thought I needed it. I did not. I should have trusted myself first. There is a finite subset A sub delta of A, so some kind of collection of points inside of A, so that all elements of X are within distance less than delta of this subset here. So the way to kind of think of the picture is that you'll have your set A, or you'll have your compact set X, and then we will choose a countable dense set inside of here. But that if I choose a delta greater than 0 beforehand, then if I use little open balls of radius delta around some of these points, then I only really need finitely many of those balls to do it, to cover the entire space, because all elements of the set X are within distance less than delta. So each of these has radii delta that is less than delta within some point inside of A sub delta. So this is essentially saying that we can do one of two things. One, we can get, if we have points that are close enough to these points here, then what we essentially get is that something that is true about each of these individual points, A sub delta, is going to be, if there's some sort of way to kind of transfer that truth statement to points that are also close by, then the countableness of this is going to be very useful. The denseness of this set is going to be a pretty big deal because now all points are going to be within delta of a finite subset even of what's going on, and we're end up unioning these countable sets over a countable index to get a countable collection for this A. And then the fact that all points are somehow close by to it, and this is what we'll see in our Arzela-Ascoli theorem, is that there's a way to transfer the truth value of certain statements, right? Convergence at specific points, like in this countable dense set, to be convergence on the entire set of X. That's going to be one of our goals and main themes of this particular video lecture, is that local data on a countable dense set is going to convert itself into global data, something that works and makes sense on the entire set of X. And this is our very first proposition to get us to that point. It says that compact metric spaces are the right domains to be taking a look at because they're separable. And what's more, you can separate them in such a way so that only if you need everything to be within delta of a certain point, then you can just take a finite subset of that countable dense set instead. And it's remarkable how short this proof is. Now, I'll want to talk about it at some length just to make sure that we kind of go through and get it. But it's maybe interesting to note that this is a lot like our last theorem in the video lecture 4-3, where we were talking about compactness. So if X is compact, first things first, it is totally bounded. Remember that totally bounded means that there is going to be a finite number of balls that cover the space for any type of radius value that you give each of those balls. So for all n and n, I'm going to choose that radius value to be 1 over n. So there's a finite number of those balls. The radius here is 1 over n. And to distinguish that, I'm kind of looking at this as a something here with a n. These centers of these balls are at some sort of value that matters with respect to what radius I'm using. I will use a superscript of n to denote that these are the centers of the balls at this particular radius. But the balls themselves are going to be indexed by I for each individual n. So x sub I n. And these are all going to cover the space of X. Well, let A be the union of unioning over all of the i's, which is a finite collection, and unioning over all of the n's, which is a countable collection. This should be a countable set, and this is the set of all of the balls. We want to show that this is indeed our countable dense set. We already shown that it's countable because it's a countable, it's a union of finite sets over a countable index. And now we just want to show that this A is indeed dense in X. So this is the set of all centers of these balls of all radii 1 over n from what we've been distinguishing here. So in order to do that, we need to show that there's a sequence of these centers of balls that gets to any point x and x. So I'll start by just putting an x inside of x. Then these balls, these b of x sub I n comma 1 over n's, fixing an n here, these balls cover x for each n. So x has to be inside of one of them. Let's say that for each n that we clarify that it is this ball that x is inside of, the ball b x sub n prime, comma 1 over n. X sub n prime is the center of the ball of which the value of x is inside. Now, this is true for regardless of the value of n. So notice in particular that the distance from x sub n prime and this value of x is less than 1 over n by the definition of being inside one of those balls. So you know what I'm about to do next. I'm about to take a limit. If I take a limit in n here, then I am taking a sequence x sub 1 prime, x sub 2 prime, x sub 3 prime of sequences of points, all of which are inside of my countable dense set A, because these are just centers of the balls that I've already defined. And they are getting closer and closer to the value of x. Their distance is bounded above by 1 over n, in which case that sequence converges to x. And that's exactly what I needed in order to show that this was dense. A pretty neat, slick proof, honestly, that shows that compact metric spaces are indeed separable. And that's a huge component of what we're about to be doing, is that we can start working on just countable collections of things and start saying that that's true about compactness. I don't know if I've even said this in a video yet, so I'll say it here. That compactness for analysts is the next best thing to finite. It is like the analyst's version of finite, because it says that compact, using our open covering definition that we've read about and maybe not mentioned in a video lecture yet, but we've read about a few weeks ago, it says that in terms of the topology on the compact metric space, any time that you take a look at a collection of open balls that cover the space, you only really need finitely many. And that's a big deal if you need to be able to say, okay, well, I'm going to generate a bunch of open sets that I know you need to give me the entire space. Being able to cut down and say I only needed finitely many of those allows us to do arguments with stuff that only require a finite number of objects. And that can be a huge deal. We know that there are very many things that don't hold true when you take a limit of infinite, like, and start considering infinitely many things. And that holds true in many of our definitions here. So we have to be very careful when we're dealing with the infinite. If we get to say, oh, we could just be dealing with this infinite, analysts just start throwing a party. They just start having a great time. So compactness is the analyst's next best thing to finiteness in terms of allowing the arguments to be as simple as they possibly can be. If they can't get compact or they can't get finite, they sometimes want countable, they want separable, they want some of these other objects as well. They're going to get everything that they can to be as close as possible to finite. And knowing what we get, how close we are to finite, allows us to know, okay, well, how can we generalize these arguments from finite sets to infinite ones? So how do we characterize compactness in some of our sets and the continuous functions from a compact set X? Well, we know from video lectures, I need to go back for here and write this as 4-3, that compact sets are exactly those which are closed and totally bounded. Well, let's start by taking a look at what balls in this space look like. I've gone here and drawn a ball around a continuous function. Remember, these are going to be the set of all functions that are inside some sort of epsilon window of this continuous function. Namely, I'm thinking of functions that live entirely inside of this little window here, all of which are continuous functions. This is something that is within 1/2 of the function sine of x minus pi over 2. This function is really, really close to this function because remember, in order to be close to a function of continuous functions, you have to be within 1/2 of it everywhere. If you're within one of it somewhere, then the distance jumps up to 1. It's taking a supremum over the differences between the functions at all possible x values. But notice something interesting about the function that I just drew. Not only is this function close to the original function, it's also close to all of the points that are close to itself. You can kind of say, okay, well then only the possible like continuity restrictions on this are also very strong. Taking a look at each slice here, the difference between possible jumps in terms of x is very, very small. It's only 1. And as you continue to shrink that epsilon window, that radius down to nothing, then the amount that a function can jump inside of this window is also very, very small. This gets us very close to the notion of equicontinuity. The one thing that's a little bit of a misnomer here that we have to add in to kind of get us to a notion of equicontinuity is that equicontinuity allows us to consider sets of functions that are also in translates of these balls. So something like this, taking the function that I had from above and then just redrawing it here and drawing perhaps another function of this form. These two functions together would be in a set of something equicontinuous. Equicontinuous means, if you recall from the previous week, it says that the functions inside of it are uniformly continuous using the same epsilon and delta regardless of the function that you choose. So that's what we mean by equicontinuity. Notice that there's no notion of boundedness here, and you'll see that eventually we want to actually add in a boundedness constraint because the translates that we take of these original functions could grow very, very big. But these equicontinuity things tell us we want these functions to be within epsilon of each other in terms of y. And in fact, we want their continuity to be very much similar in terms of this. I have to add in translates of balls to make sure that I am looking at functions that are not really close to each other at all, but still follow the same epsilon delta arguments as you look at two separate points on that space. The types of functions I'm trying to avoid in looking at equicontinuous spaces are things like this. Things that go too high or too low too quickly. They are not going along the same paths as the other ones. This is what I'm trying to avoid with equicontinuity. So that is the sort of definition that we're looking at, and in our homework, we'll try and determine what kinds of sets are equicontinuous and not. But let's simplify this notion a little bit further. We only need to describe closeness on a dense subset of our compact set X in order to describe closeness on the entire compact set X. This is basically saying that a condition weaker than pointwise convergence, that is, if you get pointwise convergence on the dense subset of a compact set, then in fact you actually have, if you add equicontinuity to the mix there, then you actually get uniform convergence on all of that. Let's talk about that for a little bit. That is two conditions that are that are pretty interesting. One is pretty weak, weaker than pointwise convergence, is pretty weak. Equicontinuity we don't know a ton about. But it turns out to be pretty strong because if you have equicontinuity, then adding it to the condition weaker than pointwise convergence gives us uniform convergence of functions. So that kind of tells us a little bit about how strong this notion of equicontinuity is. adding it to something very weak gives us something that's very strong. Let's make clear what we mean by that statement here. Let's take this lemma. Assume that X is compact and Y is complete. Our domain is compact, our codomain is complete. That kind of tells you already perhaps what we're going to attempt to do in this problem. We're going to need the fact that we have a countable dense set in our metric space to begin with, in our domain space. And we're probably going to need to converge to specific Y values in order to get something complete. Looking along in this sequence, I notice that I have a sequence that converges, but I'm probably going to need completeness to show that it's not just Cauchy, that it actually converges to a particular point. So let's keep reading here. Let G sub k be an equicontinuous sequence in this space of continuous functions. And let's assume A is a subset of X, and it's a dense set as described in our previous proposition. So basically, we're carrying over the same construction of A that we did in our previous proposition. Namely, we're going to need those A sub delta sets. We're going to need those in what's to come up here. Let's also assume that the function G sub k of A converges for all points in our dense set. That is, it's not pointwise convergence everywhere. It's just pointwise convergence on our dense set. Then, in fact, G sub k converges in the metric row. That is, it converges uniformly. That's going to be basically what we're trying to show here with this lemma. So let's go through and talk about how we can make it work. Since C of x comma y is complete, using the fact that y is complete, it's going to suffice to show that G sub k is Cauchy. So given epsilon is greater than 0, you must find a cutoff point past which the distance between all of our functions is less than epsilon. Well, let's start by looking at this. We're going to use an epsilon over 3 argument here. And you may remember us using a few epsilon over 3 arguments, especially when talking about compactness. What we're doing there is this. We're going to basically say, okay, we're going to get some closeness between the dense subset and any other elements that we want inside of our domain X. Then we're going to get closeness between our functions because of equicontinuity and how that sort of stuff works. And then finally, we're going to tie it back together to another A sub delta ball in our range space. And essentially, we're going to be able to say that what we get is a convergent sequence of G sub kx, regardless of what point X that we choose, not just the ones inside of our dense set, but that this particular sequence converges anywhere. So the goal is to first connect G sub k of X to G sub k of A, then to connect G sub k of A to something else that's really close by, and then connect G sub that something close by, maybe a G sub L of A, back to G sub L of X, and say that those two things are indeed getting closer and closer to each other, and hence there's a Cauchy operation going on. So let's see how we have to do that and use the A sub delta sets to make that work. We have here equicontinuity implies that there exists a delta greater than 0, so that if the distance between 2 points is less than delta, then the distance between the y values of some function of plugging in these points into some function in the sequence G sub k is less than epsilon over 4. And notice that where we use the equicontinuity here is with for all k. This epsilon over 4 bound works for any value of k, and that's important because the G sub k, if we just know that they're continuous, we don't get this epsilon over 4 bound for every single value of k. We only get it for one. And it's important in this argument that as we jump from G sub k to G sub L, that we have that same epsilon over 4 bound. Otherwise, things can get out of hand. That's where we're utilizing equicontinuous here. Let's choose a finite subset A sub delta, subset of A, so that X is a union of these A sub deltas here, as shown in our previous proposition. All right. So for example, without loss of generality, if our delta is not a 1 over n, we can choose a 1 over n that's small enough that it fits within this little delta window here in our x's, so that this basically is this union of finite subsets. The sequences G sub k of A for all A inside of this A sub delta converge. So because that is exactly what we mean by it converging in this subset. So there's going to be a cutoff point so that for anything past that cutoff point, the y value distance between those two G sub n and G sub m values is less than epsilon over 4 as well. So there is our jump between functions that I was mentioning. We've got the jump between points, we've got the jump between functions, and then we want to jump back to our original point. And that's exactly what we'll do over here in this last line, jumping for that function to get less than epsilon over 4 once again. So we end up with the fact that the functions G sub n and G sub m at a given point are going to be less than 3 epsilon over 4. Taking a supremum of this over all possible x using the fact that x was an arbitrary value gives us that the distance between these two functions is less than epsilon. And that gives us the cosinus that we are looking for. A neat little epsilon over 3 trick again. Notice I only used epsilon over 4, and you may have been like, why are there going to be 4 of them? No, there's only 3, but I ended up needing to take a supremum, which loses me the less than. It gives me a less than or equal to. So I used one last epsilon over 4 to make 3 epsilon over 4 less than epsilon. You could have absolutely used epsilon over 3 the whole way here. But what this is saying is you have this, for any value of x, you are so close to a countable dense set point. And that's a huge deal because you can get convergence on that countable dense set by our assumption here in this lemma. And then once you're close enough in to another function there, then you can just move on to the next thing. You can just kind of keep going. Notice that the n and m values that we're getting are n and m values that work regardless of the values of x because of the fact of equicontinuity. Equicontinuity, absolutely indispensable here. And these sorts of properties definitely do not hold if we try and do this with any other types of function. So a huge component of making this lemma work is the fact that we have a pointwise weaker than pointwise plus equicontinuity to make this work. So how are we going to use that? Well, we'll use it here. We're going to basically say, in order to show that you have some sort of compact set, you now only need to show that if you're given an equicontinuous sequence, that it converges on a countable dense set. If it converges on a countable dense set, and you already know a priori that it is going to be equicontinuous, then you can combine those two things together to get a convergent point. And notice that sequence can be anything as long as it is a equicontinuous sequence. And in this proposition here, we're going to add a condition of bounded to ensure that we get the points that we're looking for. If we get to that point, then we can say, based on our previous lemma, that we get a convergent point for this. And that's exactly what we want for compactness. Given any sequence inside of this set, then we should be able to find another sequence that converges to it. Right. So that's exactly what we're going to try and do. Let's take this proposition. Let's get our same setup as before. X is a compact metric space. And let's let f sub n be a bounded and equicontinuous. Equicontinuous, so we can use the lemma from before, and bounded because we're about to need to use the boundedness to get some convergent points on our countable dense set. Now, something interesting that's going to happen here in this proof is we're going to be using a diagonalization argument on that next slide. So be ready for that as we start getting there. So if we have this bounded equicontinuous sequence, then f sub n has a subsequence converging inside of the continuous functions. So first, let's go ahead and enumerate that countable dense subset here. So we've got A looks like this. With the same condition, we would like to find a subsequence, and I'll call it G sub k, of this sequence f sub n such that G sub k of A converges for all A inside of the A. And that's because the lemma from last slide does the rest. So that's why we have that as a particular goal. So first, let's note that we can certainly find a subsequence, and I'll call it f sub n of 1, and I'll use parentheses up in the superscript, such that f sub n of 1 of a sub 1 converges. And that's because this sequence is bounded. So the union of the ranges of the f sub n is contained within a bounded set. I should be clear there that to say that a sequence here is bounded is to mean that it's bounded in metric, that these things are all bounded with respect to each other. They're all very close. The lowest possible point of one of the f sub n and the highest other point of one of the other f sub n, these need to be bounded as a set. And the closure of the bounded set is also bounded, so it's going to be compact inside of Rm. So we are able to take f sub n of 1, or rather, f sub n an values, and look at all of this stuff. And because this is bounded, that's going to imply that the closure of the set of all these f sub n an values, that this is a compact set because it's now closed and bounded inside of Rm, which means there exists a subsequence f sub n of 1 of these, I should be saying for a 1 here, of these a sub 1 such that it converges. And it converges to a point. And we go through and use that as a point for that point on that set to converge. So there's a subsequence f sub n1 of f sub n that has the desired property, namely the desired property that, therefore, this f sub n1, a sub n, converges to a point. Okay, so let's see it here. Let's see a sub 1. There we go. So let's go through and now say, okay, well, we've done it for a sub 1, but we've got countably many elements to go. So what are we going to do? We're about to construct a table. We're going to repeat this process to find a subsequence of f sub nk that makes this work. You may remember this from what we did back to the sequence of contractions. Here we've got f1, f2, f3, f4. Then we've got f11, f2, f21, f31, f41. All of these subsequences are being formed so that f1 here, f22, f. I'm just making sure that you hear me start talking and then I start writing because I can't do both at the same time right now. So I'll get something like this, where this is just a subsequence. This converges for a1. This converges because this is a subsequence of this. This converges for a1 and a2, and you just keep going down the list. And you might now see what we want to do here. What we want to do is to, after we're done with all of this, take a collection of all of these possible diagonal values. Just take each of these to converge first for A1, then for A1 and A2, then for A1, A2, and A3 for the next possible subsequence that we form. We're just, only thing we're doing to create a new row is repeating the process of what we did before. Now we're taking that subsequence and saying, okay, well, the range of values at a sub 2 is going to be a bounded set. So we close that. It's compact in Rm. So we find a subsequence of it for which that point converges for a2, and we form the next row of this table. And we just keep going. As we go through that, we get infinitely many subsequences, but the limit of subsequences is likely nothing. So we need to go through and do a diagonalization argument to get the subsequence that we're looking for. And that's exactly what happens here. We let g sub k equal s sub k to the k with that superscript of k. Then this sequence is eventually a subsequence of each of the f sub nks. So g sub k a sub n is going to converge for each n in the natural numbers. Think for everything here, everything past the nth part, everything past the, say, for example, this row up here, for everything past that row, this function is going to be converging for a sub 3 because I'm only going to be pushing farther along in the subsequence that was given there for me in that row. So I'm going to continue converging for a sub 3, a sub 4, a sub 5, a sub 6, all the way down to whatever point I end up getting to. And notice that at the end of the day, that now convergence works for any of the points inside of that countable dense subset. So whatever that limit is something that converges for every single point inside of the countable dense set. We now have something that works as a subsequence that we can apply the previous lemma to, and that means that it's going to converge on all of the set of X. Now that's powerful. What have we done? We started with a bounded and equicontinuous sequence here. And what that gave us was a subsequence that converges. Now, what does that sound like? That was a bounded equicontinuous sequence and gave us a subsequence that converges. That sounds like a characterization of compact. So we start seeing where this starts coming from. If X is a compact metric space, then all bounded, closed, and equicontinuous sets in the continuous functions are compact. Bounded and equicontinuous was necessary, as we saw from our previous theorem, so that our sequences could be bounded and equicontinuous, and so we could apply the previous theorem. Closed, so that these limit points for which these converge actually exist inside of the set that we're working with, so that we can say that this is indeed a compact subset of the continuous functions. So this gives us a candidate for characterizing compact sets. So if we add closed bounded for our normal typical keywords for a compact set inside of Rm, and if we add equicontinuous to it, is that good enough to get a compact subset or characterize compact subsets of continuous functions? To see this, let's get a quick technical result. We've done some problems a little bit similar to this in our homework so far, but you might want to make sure that it kind of works in terms of how you're able to kind of make sense of this lemma, which basically says that if you have a sequence of points that converges to a point, and if you have a sequence of functions that converges uniformly to a function, then plugging in the sequence of points into the sequence of functions eventually ends you up where you think you're supposed to be. So if x sub n converges to a, then f sub n converges uniformly to f, then f sub n of x sub n converges to the point f of a. We're going to use that fact here in just a little bit as we characterize the Arzela-Ascoli theorem, which says that a subset A is compact if and only if it is closed, bounded, and equicontinuous. Sometimes it doesn't feel this way as you go through the second half of a proof, but we've actually gone through the harder part of the proof. Diagonalization arguments take a little bit of thought to really kind of get your head around. This one right here is going to be a bit of a kind of contradiction argument. And we're going to kind of play around with the fact that if you have something that is not equicontinuous, we already know closed and bounded should be a good part of this. So if we claim that if some subset is not equicontinuous, there's actually no way for it to be compact. So we'll go through and show this as the one direction of the theorem that we end up needing. As we've already shown the direction that goes from right to left, closed, bounded, equicontinuous implies compact. We only need to go the opposite direction. So we go by contrapositive. We negate that the set is closed, bounded, and equicontinuous. Compact sets are always going to be closed and bounded, so let's go ahead and assume it's not equicontinuous to try and derive this contradiction. Well, what is the negation of equicontinuity? I'll save you the trouble. There exists an epsilon greater than 0, so that for all delta greater than 0, some function f has 2 points inside of its domain where the distance is close enough and the distance from their y values of the two functions is greater than or equal to epsilon. Now, this only needs to be true for some function f, but you'll see here that we're going to need that function f here for a good bit. So let's start with delta equal to 1 over n. And let's get a sequence of functions f sub n with points x sub n and y sub n, such that the distance between them is less than delta, whereas the distance between those y values of f sub n, x sub n, and s sub n, y sub n is greater than or equal to epsilon. Notice that that function might change as my points change as well. If I'm changing my delta, I may get a new function. So that's why I have to put a subscript with my functions as well as with my points. With uniform continuity, we just had to change the points, xn and yn. But equicontinuity, negating that means that there just needs to be some function that doesn't work inside of that collection of functions. So I have to put an index with that as well. That's the main difference between this part of the argument and negating something like uniform continuity. Well, let's first note that A is compact. So the sequence f sub n that we're working with has a subsequence that converges. What's more, the sequences x sub n and y sub n, these are subsequences which converge in x. So they are going to have subsequences which converge. So we need compactness at both levels. We need the compactness at the set A, which is at the function level, to get a subsequence which we'll call f sub nk that uniformly converges to f. Uniformly converges because it's convergence inside of the set of continuous functions. And we need at the level of the compact metric space to get further subsequences past that of the f sub nk. And we'll call that x sub nkj for xn and y sub nkj of the y sub n that converge to their points of x and y respectively. So note that the distance between these 2 points is getting smaller and smaller to each other. That's by our construction of what these points are. So in fact, x is equal to y. They're converging to exactly the same x point. But you may notice that there's going to be a contradiction forming now. If these x values are going to the same point, then shouldn't their y values be going to the same point, since these functions that we're working with actually are converging to one function? So if I plug in f of x, where f is the uniform limit of this subsequence f sub nk, then that should be equal to f of y. But we have limits that aren't working too nicely with each other for this particular function, the uniform limit of this subsequence f sub nk. To write all that out, this is basically what that looks like. From our lemma, f sub nk, x sub nk should converge to f of x, and f sub nk, y sub nk should converge to f of y. But notice that the distance between these two values, this has to be greater than epsilon apart at all times. But the y values that they end up converging to are exactly the same. And guess what? That's exactly our contradiction. The only thing we assumed was that A was not equicontinuous. So compactness of A implies equicontinuity of A. And that's exactly what we need to finish out this proof. So this is our characterization. It says that if we want to show that a subset of the continuous functions is compact, we don't actually need to go through a diagonalization argument every time like we did with the contractions a week ago. Instead, what we can do is just say, okay, is it a closed set? Check. Is it a bounded set? Check. Is it an equicontinuous set? Check. If it is, it's compact. If any one of those three things fails, it's not compact. And that's all that we need to do to use to characterize compactness here for these continuous functions on compact sets due to the Arzela-Ascoli theorem. So let's see this in action here. I did have to add something here to this slide because the problem as written is untrue. Let's take K to be a compact subset of R to the M. And let's let F sub n be a sequence of contractions on K such that there's some point in that compact set so that F sub n of K is equal to 0 for all n. Then let's show that F sub n has a uniformly convergent subsequence. So first, we're looking at a sequence of contractions. We recall that that means that we have F sub n of x prime is less than or equal to 1 for all n. And for all x, in fact, for all values that are considered here. So we have this kind of growth constraint on what our functions can be. How is that going to be useful? Well, this sounds like it's something very similar to equicontinuity, this sort of growth constraint sort of thing. In particular, it sounds like these are all like uniformly or equilipschits, if you would. Like they all have the same amount of bound on how far they can grow at each other's at each rate. So indeed, let's go through and let epsilon be greater than 0 and choose delta equal to epsilon. Then for all n and x, for all n in the natural numbers, and x inside of our compact set K, we have that the distance between x and y is less than delta, implies that the distance from f of x minus f of y, or f sub n of x minus f sub n of y, I should say, that this distance between, for this point, is going to be less than or equal to the absolute value of f sub n prime of that function at any given point inside of this times x minus y, where z is in the interval going from x to y, and that this is less or equal to the absolute value of x minus y, and that this is less than epsilon by choice. So this tells us a little bit that we have this equicontinuity argument to go on here. The only thing that might be kind of a little bit hand wavy here is the fact that x might actually be greater than y, in which case I need to flip around what this open interval is. But this idea of the derivative kind of working into here says that essentially there's kind of like a mean value theorem happening here. That z value could actually become there could be an actual equal sign here if we wanted to, if z is the value inside of x and y guaranteed by the mean value theorem. So theirs is this particular line for this giving us equicontinuity of our set. But what about the other two? What about closed? Now, notice that I'm actually going to ignore closed for this one. Now, why is that? I have that K is a compact subset of Rn, and I'm saying that F sub n is a uniformly convergent subsequence. Uniformly convergent subsequence, but where is the convergent point? That convergent point may not actually be in the set that I'm working with, that is this sequence of contractions. It may not itself be a contraction. I'm not going to claim, I'll use a different color here. I'm not going to claim that the set that I'm working with, which is F sub n, is closed in C of K to R. And that's because I only need that it is uniformly convergent. I don't need that subsequence is something that converges inside the set. In order for it to converge inside the set, that would mean that it is equal to one of its own functions. And that's not something that I'm necessarily looking for. However, the closure of this particular collection, we want to show that the closure of this sequence F sub n is compact, for which we only need equicontinuity and boundedness. Because if we take the closure We're still going to have equicontinuity of things inside of here. We're still going to have boundedness. Closedness is not going to be adding something to us in that regard. So we'll still have equicontinuity. We'll still have boundedness. In fact, the closure of a sequence like this is not going to add that much to us. So instead, what we end up getting is still something that is a compact set. So that might be a claim that you might want to go through and just ensure, like that. For example, if a set is equicontinuous, then its closure is equicontinuous. If a set is bounded, then its closure is bounded for continuous functions. But I'll let you go through and kind of verify those claims if you would like. So let's go through and show boundedness. Now, this is where I actually needed to add this condition, because before, when I wrote this problem, I forgot about this. I need this to have some point at which all of the functions in the sequence share the same value. They all have to be equal to 0. Otherwise, they could just be going off toward infinity, and there's no reason for those to have a uniformly converged subsequence. So these all have to be tied at a specific point. So what does that tell us? That tells us that these things have to be bounded. Note, this is for boundedness here. Note that K is compact. So it is bounded. That is, there exists a ball centered at K of some radius, and we'll maybe call that radius R, for some value R, such that K is contained within this ball. It has to be contained within some sort of ball that is around the point K. Well, then what is the possible largest value of this function, of these functions f sub n? Then for all n, the absolute value of f sub n of x is going to be less than or equal to what? Well, it can only go r away from k, where in which the function is equal to 0. And so that's going to be r in terms of the x. And there's actually a way to determine how that relates to the y's, because this is going to be less than or equal to the derivatives of these functions at any given point, z, for z inside of k. And this here can be the supremum over z and k of the absolute values of the derivatives of these functions for a particular point. But that supremum is actually bounded above by 1. So this is less than or equal to r, giving us a bound for the y values of f sub n. And that's true for any sequence f sub n that we're working with there. So that gives us boundedness. Boundedness plus equicontinuity, together with saying that we're going to be closing this set up, gives us a uniformly convergent subsequence, because we're then utilizing compactness. So just to finish that off, so there's bounded, there's equicontinuity, not going to claim closedness. And so instead, I will say that f sub n bar, this set here, is compact. So f sub n, which is inside of this closed subset, has a uniformly, because it's inside of C of k, that it's in this there you go, that it's inside of this convergence sets. So it has a convergent, which is uniformly convergent subsequence. And that gives us exactly what we want. Write an S here so I don't forget about it. There you go. And that gives us our way of utilizing this Arzela-Ascoli. We'll get a couple more examples in our homework as well, but just wanted to kind of go through and show the power of some of these theorems here. Both Stone-Weierstrass and Arzela-Ascoli have quite a bit going on. They pack quite a punch because they want you to say that you can actually characterize very big statements by doing very small things. Something algebra, something even that feels a little bit more set theoretic, actually gives us something topological, gives us something about denseness. And then compactness is something that relates just back to continuity and a bounded set. That's all that we need for showing that the closure of a set is going to be compact. But that's powerful stuff right there. So hopefully you get to see some of the power of this before we move on next week into a different type of space called a normed space. We'll be talking about something a little bit different as we move into that direction. But that'll do it for me today. Thank you so much. Have a wonderful day.